Socratic math tutor here. Today we're looking at this function f, which is defined as arctan of a linear term plus a constant. And the first task is just to show that the derivative of f is this expression here. And so to work this out is pretty easy. All we do is we use the formula for the derivative of arctan of x. And that formula is simply 1 over 1 plus x squared. So hopefully you have that memorized. And so using that, we can find the derivative of f. So let's go ahead and do that. F dash of x equals 1 over 1 plus, I'm not going to write x squared. What I'm actually going to do is I'm going to grab this term, and that's the one I'm going to square. So that's going to go in here. So plus 3x minus 6 squared. And of course, because of the way the chain rule works, we also need to differentiate this. So the derivative here is obviously 3, and so therefore we need to multiply this expression by 3. And the easiest way to do that is for me to just delete this one and put a 3 there. Okay, so we can see here that our numerator is what we need it to be. Our denominator is not quite right, so we need to expand it out to get this. So let's go ahead and do that. I'll leave the numerator the same, put the 1 plus here, and then we just need to expand this guy out. And the formula we're going to use, hopefully you're familiar with it, it's the formula for a minus b squared, and it's a squared minus 2ab plus b squared. Hopefully you've got that memorized. And so we can use that to go in here and write 9x squared minus 36x plus 36. Just expand out my fraction line to make it look a little nicer. And at this point, we're nearly done. So I'm going to keep the numerator the same. Collect like terms, so 9x squared goes out the front. Then we get the minus 36x. And notice we've got a 1 here and a 36 here. So these are both constant terms. And so they're going to combine out the end. And we're going to get a plus 37 here. So just notice that that's exactly the form that we wanted. And that's how we know that we're done with part A. So for part B, we're asked to show that the graph of f has a point of inflection at x equals 2. Okay, so we're trying to show that f of x inflects at x equals 2. And that's equivalent to showing that f dash of x turns at x equals 2. So that's obviously equivalent to showing that this giant expression that we worked out earlier turns at that point. So here's the bit where we get a little bit clever. So it turns out that if we have a function like this that has a turning point at a particular x value, what happens if we graph the reciprocal is we find that it also has a turning point at exactly the same x value. Okay, so this x value and this x value match. The y value, of course, will be 1 divided by the original y value, so they're not going to have the same y values, but the x values of those turning points will be the same. And the only catch here is if our function is actually turning and touching the x-axis and then bouncing off. And the problem we run into in that context is that the reciprocal will actually blow up here. It's going to go all the way to infinity, and so we'll end up with this asymptote here. And the problem, of course, in that case is that we just don't have a turning point. So in general, the reciprocal of a function will have turning points at exactly the same x values as the original function, with the caveat that if the original function is 0 at one of its turning points, that's actually not going to be a turning point of the reciprocal, because it'll be an asymptote. So if you want a little bit more insight there and a little bit more clarity, I'm going to put a link in the description to another video where I really talk out that idea and look at different facets of it. What are the turning points of f squared? What are the turning points of 1 on f? Things like that. So go ahead and click that link if you want some more information. But at this point, we'll just focus back in on the problem and we'll continue solving the problem at hand. So let's go ahead and give a name to this denominator. All right, call this p of x. Get an arrow going there. And so on our next step, what we need to do is we need to show that p of x turns at x equals 2. and that p of x equals 2, or p of 2, let's say, is not 0. Let's call this top statement A, and we'll call the next one B. Okay, so let's break into two columns. Here I'm going to show A, and over here I'll show B. You don't have to use a two-column approach, but I think it's convenient here. So we're trying to show that p of x turns at x equals 2. And there's actually a formula that you should know for the turning point of a quadratic. So the turning point has x value negative b over 2a. And so we're trying to show that negative b, so negative 36 over 2a, so that's 2 times 9, equals 2. And this is what we're trying to show. Okay, so it's enough to show that 36 over 18 is 2. But this is trivial. So we're trying to show 2 equals 2. And so that completes that subproof. Sometimes I write a square like this to mean that a proof is complete, or you can use it to mean that a subproof is complete. This is sometimes called the tombstone symbol, by the way. Okay, so over on the right, we're trying to show B. Might as well put that a bit further left. So we're trying to show that P of 2 is not 0. So we're trying to show, okay, I'll plug 2 in. So 9x squared becomes 9 times 4, which is 36, minus 36 times 2, so minus 72, plus 37. This hopefully is not 0. And we're trying to show that, so let's combine the 36 and the 37 together. So we're trying to show that 73 minus 72 is not 0, which should be pretty obvious. We're basically trying to show that 1 is not 0, and that's trivial. Okay, so we've completed both subproofs, and therefore our proof is finished. So therefore we can say that we've proved that the graph of f has a point of inflection at x equals 2. Okay, so let's go to part C. We're told to sketch the graph of y equals f of x on the axes provided below, so these axes. And we're supposed to label any asymptotes with their equations, and we're supposed to label the point of inflection with its coordinates. Okay, so I've deleted everything we had there just to give ourselves a bit of extra space. We know that arctan of x lives in the set negative pi on 2 through to pi on 2. And that's really just coming from the graph, right? So if we graph arctan, it's going to look something like that with asymptotes at y equals pi on 2 and y equals negative pi on 2. Okay, so that's where this line is coming from. And so what we can therefore say is that arctan of x plus pi is an element of the set pi on 2 through to 3 pi on 2. Okay, so these are giving us our asymptotes for arctan shifted up by pi units, or by pi amount. And let's keep in mind that this expression in here is just moving our graph left and right, and so really that shouldn't change the range of our function, and therefore it really shouldn't be changing the horizontal asymptotes either. So we should have the exact same asymptotes over here for f as we have over here for arctan of x plus pi. And so what that tells us is that we have an asymptote at pi over 2, so I'll label that with y equals pi over 2. We have another asymptote up here at y equals 3 pi on 2. Go ahead and label that. And we already worked out that we have an inflection point at x equals 2, right? So we can go ahead and use that. Here's x equals 2. And so we know that our graph must look something like this. Okay? So let's go ahead and label this inflection point. We know the x value is 2. As for the height, what we need to do is we just need to plug 2 into this equation to get a corresponding y value. Okay, and actually, if you're a bit clever, you'll notice you don't even have to do that, because basically right in between these two values is the inflection point for arctan. So arctan has an inflection point at y equals 0. And therefore, once we add pi, the inflection point should be at y equals pi. And so we can go ahead and put pi in here. Notice it's just the average of these two. That's because it's smack bang in the middle. And so now we've got our labeled inflection point, we've got our labeled asymptotes, and that's exactly what the question asked for. So at this point, we're done.